Welcome to a comprehensive analysis of linear time sorting mechanisms. While the study of sorting is often dominated by comparison-based algorithms like Quicksort, today we explore the distinct class of distribution algorithms. We will dissect the mechanics of counting sort, its mathematical underpinnings, and its critical role in modern computational architectures.
To understand where we are going, we must recognize where we stand. For decades, algorithms like Mergesort and heapsort have been the standard bearers. These are comparison-based methods. However, they hit a theoretical speed limit. Linear time sorting bypasses this limit entirely, not by comparing elements, but by exploiting the inherent structure of the data itself.
Let's establish the mathematical ceiling. In a comparison model, every decision is binary. Is A greater than B? To sort n elements, you need to identify one specific permutation out of n factorial possibilities. Mathematically, this decision tree requires a height of at least n log n. This is an insurmountable wall for comparison sorts. To go faster, we must change the rules of the game.
Distribution sorting changes the paradigm from comparing to addressing. Think of it as a librarian organizing books. The librarian doesn't compare one book to every other book on the cart. She simply looks at the call number and places it directly on the correct shelf. In computer science, this utilizes the direct addressing principle, where a value is used as an array index, allowing for constant time placement.
Donald Knuth formalized a critical distinction between two types of counting. On the left, we have comparison counting, a brute force method that compares every element against every other, resulting in poor quadratic performance. On the right is our focus, distribution counting. This method constructs a frequency histogram to determine rank, achieving linear efficiency. The counting sort algorithm operates in three distinct phases. First, frequency analysis, where we build a histogram of the data. Second, accumulation, where we transform those counts into starting indices. And finally, placement, where we construct the sorted output array. In the first phase, we iterate through the input array. For each element, we use its numeric value as an index into our auxiliary count array and increment it. This is an O of n operation. However, it relies on a critical assumption that the value is a valid, non-negative integer index. Raw counts tell us how many, but not where. To find the positions, we calculate the prefix sums. We iterate through our count array, adding the previous sum to the current index. After this transformation, the value at index I tells us exactly how many elements are less than or equal to I, effectively reserving space in the output array. The final phase is the placement. Crucially, we must iterate through the original input array in reverse order. Why reverse? This guarantees stability. When we encounter duplicate values, the reverse traversal ensures that the instance appearing later in the input is placed in the highest available slot for that value, preserving their original relative order. The theoretical elegance of counting sort lies in its runtime, big O of n plus k, where n is the number of elements and k is the range of values. This is linear time. However, there is a catch. The space complexity is also proportional to n plus k. If the range k becomes significantly larger than n, the algorithm loses its advantage and can even become slower than basic quadratic sorts.
This algorithm is not a silver bullet. It faces strict limitations. First, negative numbers require an offset mapping to shift them into valid array indices. Second, floating point numbers cannot be used as indices directly. For those, we need bucket sort. Finally, if the range of the data is massive, say 64-bit integers, the memory requirement for the count array becomes physically impossible.
Modern performance is dictated by memory hierarchy. While counting sort has a low instruction count, it suffers from poor cache locality. Accessing the count array involves random jumps in memory. If the range k exceeds the CPU cache size, the processor stalls waiting for data from the main RAM. In these scenarios, a cache-friendly algorithm like Quicksort often wins, despite having a higher theoretical complexity.
How do we handle large numbers? We use Radix Sort. Instead of sorting the entire number at once, we decompose it into digits or bytes. We perform a stable counting sort on the least significant digit, then the next, and so on. This keeps the range k small, usually just 0 to 9 or 0 to 255, keeping the count array entirely within the fast CPU cache.
Parallelizing this algorithm is tricky due to race conditions. The optimal strategy uses a local histogram approach. We partition the data, and each thread counts its own chunk privately. We then merge these into a global histogram and calculate offsets. This allows threads to write to the output array simultaneously without locking, provided they know exactly where their slice belongs.
Comparing the two champions, Counting Sort wins on raw operation count and stability, but it pays a heavy price in memory usage. Quicksort, while theoretically slower in instruction count, is extremely memory efficient and cache-friendly. Counting Sort is the specialist. Quicksort is the generalist.
Despite its limitations, Counting Sort is the engine behind many high-performance systems. It is used in bioinformatics for DNA sequencing, where the alphabet is small. It powers image processing tools for histogram equalization. And it is a fundamental step in data compression algorithms, like Huffman coding. It remains a vital tool in the computational scientist's arsenal.